quantumlaserpointers.com.
Quantum Laser Pointers brings you the infamous double-slit experiment right in the palm of your hand. In 1801, English physicist Thomas Young performed this experiment to determine if light was a particle or a wave. A laser shines a coherent beam of light through a film disc containing two parallel slits. Light striking the wall behind the slits produces a classic interference pattern. This surprising result means light passes through the parallel slits not as particles, but as waves.
Visit our website or subscribe to our YouTube channel now. Be among the first to see our new line of double-slit lasers, quantumlaserpointers.com.
Particles from the world's first moments, protons, neutrons, electrons, but others too, much more energetic. They disappeared very quickly after the Big Bang and no longer exist today in their natural state. The only way of identifying them, recreating a mini Big Bang and trying to reproduce these particles which lie at the very origins of our universe.
The point of using accelerators is to try to get the maximum energy out of the accelerator. If you accelerate electrons, you accelerate protons, you accelerate ions, you want to get the maximum energy.
This picture is not fiction. It represents what's been happening for several years in the lab. But the energy necessary for the experiment can only be increased beyond a certain threshold in the lab by technological artifice. Indeed, the faster the electrons and positrons travel, the more they generate their own braking system by emitting light.
The problem with electrons and positrons is that they lose a large amount of energy by synchrotron radiation. So at each turn of the machine, the electrons and the positron had to be reaccelerated with very strong fields. And the only way to do it was to use superconducting cavities. At each turn of the particles, they would get a kick of about 3 giga-electron volts. That means 3 gigavolts. And in order to do that, in the machine were installed 288 superconducting cavities operating at 4.2 Kelvin and with a field of about 6 megawatt per meter.
If you have a normal metal, you cannot really get so high in energy because the power consumption will be too high, and take out this power will be extremely difficult over the central threshold. Instead, if you have a superconducting material, the losses are much less. If you look at this expression, a good metal and a good superconductor do not go well together. If you have a very good metal, is copper or silver, they are not superconducting. So you have to find a compromise between having a good superconductor with ITC, but also good metal. So you need these two parameters, often in contradiction. If you take niobium-13, niobium-13 is a very good superconductor, but it's not as good as a metal. So you need a metal that is not only a good superconductor, but also has a very good thermal conduction. So if you use an alloy, the thermal conduction will always be much worse than in a pure element. So the only strategy to make a bulk cavity designed in this way is essentially to use niobium. It does not emit electrons and is very resistant to radiation damage. This is the type of material you really want to use. Consider that the LEP accelerator in Geneva has about 288 modules of 4 cavities.
A giant accelerator 100 meters below ground in a 27-kilometer long circular tunnel.
If you do that all by bulk niobium, the overall weight of niobium is something like is close to the overall production of the world of niobium for 1 year. Copper cavity. And the copper cavity can be done with the same techniques. Can be welded, can be hydroformed, or can be spinned. The best will be spinned. So you do a copper cavity, and then you find a way of depositing inside the cavity a thin film of the superconductor. And you only use niobium for a thin film coverage that will be, and it's not like millimeters, it will be microns. So the cost will drop. The overall cost reduction is $27 million. An accelerator, you have hundreds of cavities to accelerate the beam, and the cost of the material can be important. Magnesium diborite is inexpensive, It's very light, very ITC, is 40 degrees, and it's a very good metal. But the real bad news came when this two-gap story came out. I mean, this is a very ITC material, but this in fact has a complicated electronic structure and has two gaps. And so you have a small gap in one band, it's the pi band, and in this band, as soon as you have enough energy to overcome this gap energy, you produce excitation, quasi-particles, or normal electrons, we call them, and this will dissipate. And so the material will degrade its property.
To be able to create a more energetic collision, capable of generating heavier particles, a completely new machine had to be designed. It's the LHC, a much more powerful accelerator that will be installed in the same 27-kilometer circular tunnel. Instead of propelling electrons and positrons, the LHC will accelerate protons, 2,000 times heavier. The physicists hope to be able to identify in the products of the collision particles which explain the origins of our universe.
For accelerating protons, in principle, you don't need superconducting cavities because they don't lose much energy by synchrotron radiation. However, it will use anyway superconducting cavities because superconducting cavities have an advantage, can be made with very large apertures. So that means that the beam pipe can be made very large, and this is very good for the stability of the particle beams.
In this 27-kilometer circular tunnel, whose radius can obviously not be modified, the challenge consists of circulating two opposite beams of protons at more than 300,000 kilometers per second in successive bundles, whilst maintaining the protons precisely at the center of the tube containing them. The ultimate objective is to bring about a frontal collision of these bundles of protons in 4 different places, having deviated them from their trajectory to obtain an interaction at the center of the detectors.
Seven times more powerful than Fermilab.
The only foreseeable solution to maintain the particles in their trajectory is to create a powerful magnetic field along the full length of the proton's route. To guide the two opposite waves of protons in the LHC, a complex magnet has to be built. Moreover, an LHC magnet made with traditional materials such as copper would need to be supplied by several power stations, a veritable utopia. In addition, traditional electric cables would not support the necessary intensity of current. The material chosen for the LHC is niobium titanium, which is superconducting at the temperature of liquid helium. It has the indispensable mechanical resistance qualities required to resist the configurations designed by the LHC engineers. Moreover, to improve the performance of the magnet, it's been decided to use helium at -271 degrees Celsius. At this temperature, helium becomes superfluid and conducts heat perfectly. It no longer seems to be subject to the phenomenon of gravity, infiltrates everywhere, and can therefore completely immerse the superconducting cables and thus evacuate the heat perfectly. But how have these superconducting cables been assembled to form the LHC magnet? The genesis of an invention. In order to accelerate two waves of protons circulating in opposite directions in a machine which is both compact and necessitates a minimum electric power, the engineers have succeeded in designing a magnet capable of ensuring the simultaneous guidance of two bundles of protons moving in opposite directions. An explanation of the principle. With two opposing currents, you obtain a stronger field, which is better oriented in the useful zone between them. By increasing -I and +I, you increase the force in field B. We can observe that the lines of the field are closer together. In correctly choosing the geometry of the conductors carrying the currents, -I and +I are able to create a uniform magnetic field in the useful zone. Nevertheless, the lines of the field close again, far from the useful zone. Thus, a parasitic field has been created outside the useful zone.
As you see, for example, here we have the current going in, coming out. This is a sinusoidal distribution. And you see here, for the first order, you see a very homogeneous electromagnetic field. Of course, I might just quickly mention that we have not only bending magnets, dipole bending magnets, but also quadrupole magnets, which are used to focus the beam. We cannot approximate such a current distribution. We want to wind the coil from superconducting cables. Here we have an example. This is carrying about 11,500 amps. What we can do is we can try to approximate this ideal shape by, for example, a number of shells of superconducting cables, or by so-called coil blocks, which we then can shape with, by means of mathematical optimization routines. We can try to shape these coil blocks in such a way that we have a relatively homogeneous field in the aperture as well. Of course, you see where the limits of the method are. We are not as homogeneous as we would be for the ideal case. If you look at the equation here, basically the resolution depends on the sag of the particle, on the sag of the particle's trajectory, and this is related to the maximum achievable field in the magnet and the length of the particle's trajectory to the square. So here it pays off much more to create a very large volume with a medium field. This having said, of course, medium field is for Tesla, which is still, if you think about electrical motors or any other applications, this is still very, very high.
The action of the magnetic field on currents -I and +I translates into electromagnetic forces -F and +F, which tend to open the magnet. 400 tons per meter. To contain the action of these forces, the conductors which carry the currents are fastened in collars made of non-magnetic material. By surrounding all the conducting collars in a yoke made from a magnetic material, iron for example, the lines of the field are confined, and thus parasitic magnetic fields are avoided, without affecting the field in the useful zone inside the tube, shown in white, in which there's a perfect vacuum. To bend the two bundles of protons circulating in opposite directions, we need two equal and opposite magnetic fields in the two neighboring useful zones. We therefore combine two sets of conductors in tightening collars and a common yoke. Thus combined, the system can function. Finally, the assembly composed of conductors, collars and yokes is inserted into the cylinder, which ensures the mechanical rigidity of the system and plays the role of a tight container for the liquid helium in which the entire structure is immersed. Strength, crack resistance, but also perfect tightness. Indeed, 700,000 liters of liquid helium will be injected into the machine and no leaks can be tolerated. Each dipole is 15 meters long. This means that problems at joints, in terms of both current and helium flow, had to be solved with extreme care. In fact, some 1,200 dipoles have to be interconnected in the tunnel. The continuous feeding of liquid helium has to occur all along the 27 kilometers of the machine's length.
For the series of current leads for the LAC machine, we need to build an enormous number of current leads, about 3,000 in total, because we need to transport more than 2 million ampere of current into the coil mass.
It necessitates giant cryogenic units to produce and conserve the cold with absolute guarantee of safety. The helium in gaseous form is stored in huge reservoirs, then compressed by powerful compressors. In the assembly hall, a complete magnet with its tightening collars is placed in the yoke. Once assembled, the dipole will be introduced into a giant press in order to compress the elements and weld them. This press, which exerts a pressure of 900 tons per meter, has another function, slightly bending the dipole to give it a shape compatible with that of the circular tunnel.
there we will need even stronger fields than we have now, and we have to take care of the enormous radiation which is coming out of the detectors due to the collisions. So all the concepts which we have in the moment to design such magnets have to be revised.
Let's focus first on this 11 Tesla magnet we designed. We started the design in the early 90s as an answer or an alternative to the niobium titanium magnets for LHC. So at that time already it was clear that niobium tin could not replace niobium titanium for LHC at the first generation, but there had to be technology following up niobium titanium. And for the moment still niobium tin is the only alternative. So that was also our motivation to break through the, let's say, the natural barrier for niobium titanium magnets, and that's about 10 Tesla at 1.9 Kelvin. So our idea at that time was, okay, we do not have to go immediately to 13, 14 Tesla because that's out of reach, out of any experience. Just break niobium titanium. So that was our motivation, and of course we started in an LHC kind of design. So twin aperture magnet with things learned from the mechanical design and the magnetic design for LHC magnets. But of course we immediately were aware that we encountered new problems, completely related to the fact that niobium tin is a brittle material. You have to heat treat the coils that are wound. So after you have made the coils, you have to heat treat them at 700 degrees, so that's very difficult from an engineering point of view. And again, if you increase the field and the current density, of course, in the coils, then the Lorentz forces also will increase quadratically with the field. In red, you see that there is an enormous force tending the coils to be pushed outwards. So you need to sustain this force and to keep the coil into shape. At the same time, and this force is high, it's 7.5 meganewton per meter, length of coil. At the same time, the coils the two halves are pushed together here with a force of 1.6 meganewton per meter. And for niobium tin coils, this is the most dangerous one, the green one. So it's a force pressing on the cables, pressing on the individual strands in the cable. Also very difficult, by the way, to make good, highly compacted tin cables because you destroy these beautiful strands during cabling, because cabling is a horrible process, compacting the things in these flat Rutherford cables. So afterwards you do the impregnation. So all these steps had to be re-engineered, re-exercised, so we had to do that. So it took about 3 years only to make all these steps into a kind of successful dummy coil, and successful in engineering sense, so not in the performance sense of the coils. So we had only one chance to build it and to test it. So we had to incorporate a lot of diagnostics, so many voltage steps, thermometers, strain gauges and things like that. And also for the CERN people that was a naughty surprise, because we came up with a magnet finally in the test station at CERN with about 300 wires coming out of a magnet, and they expected only about 12. So also there we had it was a new exercise for the station at CERN to test this magnet. So this is the actual magnet we tested. So this is the 11 Tesla magnet, the dipole magnet with the coils inside. The only thing you see here on the outside is the mechanical support structure. Support system to take the actual forces. Here you see 8 rods running through the whole magnet from one side to the other to take the enormous actual forces exerting on the coils. This whole thing is immersed into a cryostat, into liquid helium, and operating at 4.2 K. So we proved that it can be done. So we have taken with this 11 Tesla a lot of prejudices away against niobium tin magnets, large-scale magnets. So that was very important.
To higher collision energies, presently the LHC design is for 8.3 Tesla. When you want to do something in the same tunnel with about the same size, you have to go to 15 Tesla or even to 20-25 Tesla. Right now we already have exotic magnets designed with niobium tin and HTS conductor for 25 Tesla. It is a way to go. It will take another 15-20 years, but it's possible.
The machine was installed 288 superconducting cavities operating at 4.2 Kelvin and with a field of about 6 megawatt per meter.
If you have a normal metal, you cannot really get so high in energy because the power consumption will be too high, and take out this power will be extremely difficult over the central threshold. Instead, if you have a superconducting material, the losses are much less. If you look at this expression, a good metal and a good superconductor do not go well together. If you have a very good metal, is copper or silver, they are not superconductors.
And trying to reproduce these particles which lie at the very origins of our universe.
The point of using accelerators is to try to get the maximum energy out of the accelerator. If you accelerate electrons, you accelerate protons, you accelerate ions, you want to get the maximum energy.
This picture is not fiction. It represents what's been happening for several years in the lab. But the energy necessary for the experiment can only be increased beyond a certain threshold in the lab by technological artifice. Indeed, the faster the electrons and positrons travel, the more they generate their own braking system by emitting light.
The problem with electrons and positrons is that they lose a large amount of energy by synchrotron radiation. So at each turn of the machine, the electrons and the positron had to be reaccelerated with very strong fields. And the only way to do it was to use superconducting cavities. At each turn of the particles, they would get a kick of about 3 giga-electron-volts. That means 3 gigavolts. And in order to do that, the
Blitz produces a classic interference pattern. This surprising result means light passes through the parallel slits not as particles, but as waves.
Visit our website or subscribe to our YouTube channel now. Be among the first to see our new line of double-slit lasers. QuantumLaserPointers.com.
Particles from the world's first moments, protons, neutrons, electrons, but others too, much more energetic. They disappeared very quickly after the Big Bang and no longer exist today in their natural state. The only way of identifying them, recreating a mini Big Bang.
QuantumLaserPointers.com.
Quantum Laser Pointers brings you the infamous double-slit experiment right in the palm of your hand. In 1801, English physicist Thomas Young performed this experiment to determine if light was a particle or a wave. A laser shines a coherent beam of light through a film disc containing 2 parallel slits. Light striking the wall behind the